We've been dealing with trigonometric substitution lately, and I have this area problem for us. So I have this circle over here with a radius A, and then I've cut out a little piece out of it, and this height here is B, and what we want to do is find the area of this piece here in orange. So why don't you pause the video and work on this? All right, assuming that you've given it a go, I think our first order of business here is to figure out, okay, how do we want to integrate? Do we want to integrate with respect to y, or do we want to integrate with respect to x? And I'm going to argue that we're going to want to integrate with respect to y. And that's because if we integrate with respect to x, we're going to run into this corner over here, and we'll have to set up a separate integral to deal with this curvy part. So integrating with respect to y is going to be our best bet. And now we need to get this equation of our circle in terms of y. So we're going to have x squared is equal to a squared minus y squared. And then taking the square root of both sides, we have x is equal to plus or minus the square root of a squared minus y squared. And now we can construct our definite integral. So we're going to have the definite integral. Wow, let's try that again. The definite integral from 0 to b. All right, and then our integrand is going to be this positive root. Our tab over here is only in where x is positive, so we're taking the positive root. So I have the square root of a squared minus y squared, and then we're integrating with respect to y. This is our definite integral, and now we need to solve it. And it is just screaming out to us, please use trig substitution. And we're going to do that. So trig substitution, we need to figure out what we're going to end up using here in terms of trig identity. And it looks like to me, we're going to want to use this fact. We're going to want to use that sine squared plus cosine squared is 1. And then just out of personal preference, I like taking the derivative of sine better than cosine because then I don't have to deal with a negative sign. So I'm going to use this ultimately, that cosine squared is equal to 1 minus sine squared. 1 minus sine squared. And if we're going to use that, then we're going to let y be equal to a sine of u. And now differentiating both sides, we get this. We get dy is equal to a times cosine of u du. And now we can move forward and put together a definite integral, or we could get some new limits of integration. And just a quick side note on that, as you work through more of these problems, you might notice, okay, we're going to have a lot of trigonometric substitutions going on here. This is going to be a longer problem. Maybe we'll hold off on the new limits of integration and end up back substituting to your original variable, which in this case would be y. So in this case, if you're doing that, you wouldn't get new limits. You would just go through, evaluate, back substitute to y. That can work. In this case here, I think it might save us some time to get some new limits, but just work through that and get some experience, whatever you feel comfortable with. So let's get some new limits. Let's get some new limits and see if this saves us some time in the long run. So our new limits of integration, our upper limit is originally y is equal to b, and our lower limit is y is equal to 0. And then under our substitution, we get what? We get u now as our upper limit is going to be equal to, we're going to let y be b, so we're going to have the inverse sine of b over a as our new upper limit. And then lower limit, let's see, u is going to be equal to, well, that's just going to be 0. That's great. So we have our new lower limit here is 0. So let's put together our definite integral now. Our definite integral is going to be from 0 to the inverse sine of b over a. And then our integrand is what? Scrolling back up here, we have the square root of a squared minus y squared. So then under our substitution, that's going to be the square root of a squared minus a squared times sine squared. That is going to be what's under our radical. And then we'll still need to fill in dy. But let's start working on this. So this is going to be the square root, we said, of a squared minus a squared times sine squared. All right. And then we still need to get dy in. And dy we found to be a times cosine of u du. So this is a times cosine of u du. This is our definite integral under our substitution. And now let's keep working on this. We just need to simplify a little bit, and then we'll be able to anti-differentiate and evaluate. So let's do that. Let's see here. It looks like we can factor out an a squared. And then we could take the square root of that, and that would be just a. So a would come out of this. So we'd have, let's start getting that down. We're going to have definite integral from 0 to the inverse sign of b over a, okay? And then we said we could take out an a squared, and taking the square root of that, that's just going to be a. And then we're still left with the square root of 1 minus sine squared. 1 minus sine squared. And then we're still multiplying by a times cosine of u du. Now, the whole reason why we made this trig substitution is that we could use this trig identity. We know exactly what this is. This is cosine squared. This is cosine squared. And then taking the square root of that, that is just going to give us cosine of u. So, writing this down, we have the definite integral from 0 to the inverse sine of b over a. And then we're said that we're going to have a, and then this is going to go to cosine of u. So we're going to be left with a squared times cosine squared, and then we have du. So this is what we have left. And then lastly, we're super close to being able to anti-differentiate and evaluate. We need to work on this guy right here. So maybe we can scroll up a little bit, grab some space, and remind ourselves what cosine squared we could rewrite that as. So this is another trig identity. This is that cosine squared we know is 1 plus cosine of 2u over 2. So let's fill that in, and that should help us anti-differentiate. So filling that in, we're going to have the definite integral from 0 to the inverse sine of b over a. And let's actually take this a squared out. It's just a constant, so we can throw this outside of our integral. And we said that cosine squared is this right here, 1 plus cosine of 2u over 2. And then we're still integrating with respect to u. And now it looks like we can finally anti-differentiate and evaluate. We're going to get the following. We're going to have a squared times, and anti-differentiating, we have 1/2 u, and then plus sine of 2u over 4. And you could use u substitution to get this, but just differentiate this right here, and you'll see that you'll get cosine of 2u over 2. So this is what we get, and then we need to evaluate at our lower and upper limits. We have inverse sine of b over a. And now, what do we get? We have a squared. Let's do this. A squared times the quantity 1/2, and then looking at our upper limit, so this is going to be times the inverse sine of b over a, okay? And then we have plus, and this guy looks like to be a little bit of a problem, but we do know another trig identity. We know this. We know that sine of 2u is what? Is 2 times cosine of u, sine of u. So that will help us. That will help us out. So we're going to use that. This is going to now become 2 times cosine of u times sine of u. And now this right here, 2 over 4, that's going to go to 1/2. So we're going to have plus 1/2, and then cosine of this. So cosine of the inverse sine now of b over a, and then we're multiplying that by sine of the inverse sine of b over a, which is just b over a. So this just becomes b over a right there. And now we have one other little ingredient to put together. We can make this look pretty nice. And how do we do that? Well, we could say that we could define an angle theta. We could say that theta is equal to the inverse sine of b over a. And what we could do then is say, okay, sine of theta then is equal to b over a. And what we could do is make a right triangle, and then we could find what cosine of that right triangle, cosine of theta under that right triangle is. So this is pretty cool. Here we go. Let's make a right triangle, and that will help us get a little nicer answer. So this is theta then, it's a right triangle, and then we have opposite over hypotenuse, so this is b, and this is a. And then under the Pythagorean theorem, this side right here is just a squared minus b squared. All right, the square root of a squared minus b squared. And now what is cosine of theta? Cosine of theta, adjacent over hypotenuse. And we could fill that in now. Let's do that. So we have a squared times this whole quantity, 1/2, times the inverse sine of b over a, and then plus 1/2. And then cosine, we said that this right here is theta. This right here is theta. So cosine of theta is what? Adjacent over hypotenuse. So this is the square root. This is the square root of a squared minus b squared. And then we have over a. And then we're still multiplying by b over a. We still have that b over a. B over a. And one more parentheses. Okay, and this is our answer, and now we can continue to simplify this just a little bit more. All I want to do now is distribute this a squared term, and that will be our answer, it looks like. So this is going to be a squared over 2 times the inverse sine of b over a, and then a squared to this term here. We have a squared in the denominator, so that will cancel. So we just have 1/2, and then times b times the square root of a squared minus b squared. And this is our answer right here. This is our answer right here. All that work for this guy. And why I love geometry problems so much is that we can actually make sense out of this answer now. If we go and take our answer, we take this guy right here, and let's scroll up, and then we can look at our picture and make some sense out of it. So what is this answer really saying? That's what we want to know. And then we'll be done. What is this answer really saying here? Let me grab a new color. So let's grab some blue. And let's break down both parts of this answer. So this part right here, what is this? Well, if we were to come over here and draw this, name this angle theta, this first part of this answer is the area of this sector here. So this is the area of that sector, of this circle. And basically, it's just a fraction of this whole area of the circle. So the whole area of our circle is what? It's pi times r squared. So that's going to be r is a. So that's pi a squared. And then we just want a little fraction of this area. And that fraction is theta over 2 pi. Over 2 pi. And then these pi's cancel. And we're left with a squared over 2 times theta. And what is theta in this here? Well, if we were to drop this vertical here, this hypotenuse of this triangle that gets formed is a, that's the radius of our circle, and this height here is b. So if we were to take this would be sine of theta is b over a, and then take the inverse sine of that, and we'd find that theta is the inverse sine of b over a. So this is a squared over 2 times the inverse sine of b over a, and this right here is exactly the first part of our answer, and that's, again, this area. Now, I bet you could guess what this second part of our answer is. This second part here is going to be the area of this triangle. Isn't that cool? The area of this triangle. So let's pull this triangle out and work on it a little bit. Area of this right triangle. Area of this right triangle here. This height is b. And then this hypotenuse here is, again, the radius of our circle. So that's a. And then by the Pythagorean theorem, we have what? The square root of a squared minus b squared, and then finding the area of our triangle is what? 1/2 times our base, which is b, times the height of this triangle. So times the square root of a squared minus b squared. And then you add both these together, boom, we have our answer right here. So it's cool that we can make sense out of our answer using this geometry problem. And again, I hope you got some more practice and familiarity with trig substitution.